Okay, thank you very much for joining us today, everyone. My name is Joe Steele. I'm the Senior Director of Communications and Legislative Affairs with LIFT. I want to welcome you to our summertime edition of our Liftoff webinar series. We're proud today to welcome DANTE Solutions to talk about simple, accurate, cost-effective heat treatment simulations. We have Jason Meyer on the call from DANTE Solutions, so you get to hear from him in just a second, but I do have a couple of housekeeping items to take care of before we really get rolling. We are recording this session, so please put your computers or phones on mute. I think everyone's automatically muted, but just in case, make sure that you are. So we reduce all the background noise that we can. This webinar will be posted on our website at lift.technology a little bit later. So you can go ahead and review it there or pass it along to folks who you think may be interested in the topic that was discussed today. Also, we will have a Q&A session at the end of the webinar. So please use the Q&A function that's available on the Zoom taskbar, the menu bar at the top of the screen. Well, it's the top of the screen for me. Maybe it's the bottom of the screen for you. But to use the Q&A function there, I know we are all too familiar with Zoom these days and other virtual platforms. So hopefully everyone is remaining safe and well as we hopefully are coming out of this this pandemic that we've been in for the last 18 months. So yeah, go ahead and we'll facilitate the Q&A session afterwards. I do want to spend a little bit of time and talk about LIFT for those who may not know who we are and what we do. LIFT is one of 16 National Manufacturing Innovation Institutes. We are supported and sponsored by the Department of Defense. We are based in Detroit, and we are a public-private partnership between industry, academia, and government. Nonprofit organization. Our goal, we are a membership-based organization as well. Our goal is to connect materials, processes, and systems, what we call smarter manufacturing, to drive America into the future of smarter manufacturing. So we believe that our national security and economic resiliency rests on smarter manufacturing. And our goal is to help make that happen for the United States of America, because we believe that the next industry and economic powerhouse will be the area or region that tackles that first. So we are here to help facilitate that. So how do we do that at LIFT? We are solving what we call the manufacturing equation, or working to solve what we call the manufacturing equation, the connection between materials, processes, systems, and talent. Want to make sure that the materials are in place for the right process, and we know what's going to happen to them as they're processed, so we can better predict that they will achieve success in whatever system they are being implemented in. And underneath all of that, we want to make sure that we have the talent in the manufacturing workforce that has the skills, knowledge, and abilities to handle all of those things. So we do that via two programs at LIFT: our technology program, Leading Innovations for Tomorrow, and our talent program, Learning Innovations for Tomorrow. So on the technology side of the house, we have four pillars of technology that you see on your screen now, from ICME, Integrated Computational Materials Engineering, to agile and smarter manufacturing, to advanced alloy and process development, to multi-material joining. I know you'll hear some of those things today from DANTE and what Jason is gonna speak to. So our membership base is well versed in all of these pillars of technology. I'm not going to quiz you on the screen in front of you now, but you see how deep we go into each of those areas. So if you have questions about those, please go ahead and reach out to us directly. You can contact us via our website. Have some contact information at the end of the presentation here as well. On the talent side of the house, again, it is about innovation. It's about new learning tools, pathways, and venues. And you'll see the four kind of focus areas on the screen as well. We have developed a curriculum called Ignite, Mastering Manufacturing, really a foundational curriculum, starting high schoolers to really show them what the world of advanced manufacturing engineering looks like. That is facilitated for us at our LIFT Learning Lab that you see on the screen here. It is inside our Detroit facility that you see behind me. It is perched above our high base. The students, when they come in pre-COVID, we're hoping to have the students back next year. When they come into the lab, they can look out and see all the work that's taking place in our high bay, which is fantastic. We got a 100,000 square foot building, a lot of work going on there. you know, using all the pillars of technology we just took a look at. So along with the high school students, providing them with exposure to advanced manufacturing, we also offer certification courses for jobs that are available today in things like welding, CNC operations, robotics, industrial technology and maintenance. We do that out of our facility at Lyft. We also have a program called Operation Next, which is growing across the country. That was established as a program to help military men and women earn their credentials in some of the most in-demand jobs as they leave the military, before they leave the service. So we don't just say thank you for your service and good luck finding a job. We want to help them transition into civilian careers with some of these most in-demand jobs, utilizing some of the skills that they learned in the military. So that's available at Fort Campbell, Kentucky. It's available at Michigan National Guard and Reserve, the Florida National Guard and Reserve, and stay tuned for some more announcements of that expanding across the country. So I did mention we are a membership-based organization. What do you get out of becoming a member? Well, you get to be like Jason today and present on these webinars to talk about some of the work that you're doing, but you also get to see these 7 items in action as well. You get to get the advice and counsel from Lyft. We're a nonprofit organization. We're not here to sell any specific service or product. We want to give you the best advice possible as it relates to transitioning towards smarter manufacturing. Technology accelerator, as I mentioned, using those pillars of technology, trying to connect the good ideas that come out of early research towards commercialization, cross that valley of death. We want to make sure we take those good ideas and move them forward into the marketplace. Technology showcase, I mentioned the 100,000 square foot facility, the high bay we have here. Please come visit us in Detroit next time you are in town. Please do that. You can also walk through our facility using our virtual tour that's on our website. Connector and convener, that's why we're all here today. So thanks for joining us. We want to bring the best minds together to move the manufacturing ecosystem forward in this country. Talent developer, again, we talked about that, from high school students to veterans to incumbent workers. We are trying to close that skills gap and make sure that the manufacturing ecosystem has the talent workforce needed to move forward. And finally, we are a government partner. The federal government and the Department of Defense can be unwieldy to work with. They are large organizations. How do I get in? How do I start working with those guys? We can certainly be the conduit to help you do that. So reach out to us with any questions, any comments, would you like to become a member? Yes, we'd love to have you. So please reach out to us, telephone like olden times, or via email on our website. You can also follow us on our social media channels. We'd be happy to have you there. So that is it from Lyft, just in a nutshell. You guys did sign up today to hear from Jason, so I'm going to stop sharing my screen, allow Jason to share his, and we will hear from DANTE Solutions. So Jason, the show is yours.
Thanks, Joe. Appreciate it. Let me share my screen here. And while I'm doing that, I want to thank you guys for joining me on your lunch break here. Hopefully you guys should see the presentation in front of you. And so we're saying heat treatment modeling here using DANTE Utilities. So I'm going to start out with a little bit of a introduction to DANTE here. Brief introduction. We were founded in '82, and we were part of a large collaborative effort between industry and academia between '92 and then 2000, so in the '90s, to work on predicting distortion and in heat-treated steels. And we built the computer software and everything around that time. And we had a name change from Deformation Control Technologies, which what it was originally was, to DANTE Solutions in 2014. And DANTE is an acronym. That's why you usually see it all capitalized. It stands for Distortion Analysis for Thermal Engineering. And our main lines of business are the software licenses that we develop. And then we also do heat treatment technology development, and we do consulting services with our software. Now the software itself is a software tool that connects into Abacus Mechanical or ANSYS Standard, or Abacus Standard or ANSYS Mechanical. And it's been validated for industrial uses for process design, troubleshooting, and the design of experiments. A lot of the processes and capabilities that we have are pretty much everything you see in the heat treatment. We do carburizing, we do nitriding, we do like heating as far as like slow furnace, or we even do fast ones like laser and induction heating, which goes with tempering and everything like that. We do pretty much all types of quenching, press quenching, intensive quenching, spray quenching. Any way you quench it, you can pretty much model it. And then all the normalizing and cryogenic treatments. If you're doing tempering and stuff like that, we can handle that with the software. Here are some of the examples of parts that we've used over the years. We do some carburized and press quench aerospace gears. We do have some complex powder met parts. We do some induction heating using for crankshaft using like a power density. And then we do gear shafts, and we do bevel press quench. You can see these gray things are actually the press being applied to it while it's being quenched. And then we can do immersion quenching. Like this is an immersion quench of a landing gear. You can see it's about halfway up, and the red dictates the higher heat. And then here's some customer references that we work with. As you can see, it's a lot of aerospace, automotive, agricultural, even gear manufacturers themselves, also heat treaters themselves, and academia. We do a lot of work with universities around the States. So the DANTE software models, you can see this is the general form here. And we get this information, we fit these parameters based on dilatometry data or TTT, CTT curves. We prefer dilatometry because it does include the transformation strains that you cannot get normally with the TTT diagram, and then also the Martensite start. You can't get that on the isothermal TTT diagrams. So usually that information is input given when we fit from TTTs and stuff like that, and we fit to the parameters here. We also have a multi-phase internal state variable model that accounts for each phase, the proportions of that. That'll give us the hardness and the hardening recovery. Includes a mixture law in here as well. So this is kind of like how it works, a little bit of the background there. And then the material database. We've had over 30 years of development and parameter fitting here to get these materials fine-tuned to where we can pretty much use them right away. You can see it's got all the popular grades here, like 10XX, 40XX. And the XX here means that it's a carburizing grade. And we can do like 4120, 4140, 4160, and so on, based on this main material. And inside each one of these folders is information on phase transformations, thermomechanical properties, carbon diffusion and nitrogen fusion, and microstructural and alloy effects. So that's all built in here. We also have the ability for the user to create their own materials using some of the fitting tools that we have available. And you can customize it to whichever one you need, pretty much, given the experiments. Now, the summary of today, what we're going to be covering is our utilities. So a lot of that has to do with the previous stuff has to do with the full DANTE package that plugs into Abacus or ANSYS. But we've made it more accessible so they can use the material database using these standalone programs that we came up with called utilities. So the first ones we're going to go through are going to be our carburization and nitriding ones, VCarb, GCarb, and GNitro. VCarb is a vacuum pressure, low pressure carburization process. GCarb is for gas, traditional process, and then gas nitriding in order there. We also have a TTT, CCT, and CHT generators, which will generate those little C curves that you saw earlier, and I'll go through those and how those work in a little bit. And those diagrams are good for checking the parameters and making sure everything looks right. We also have hardenability tools such as a geometry predictor and a DI predictor. The geometry predictor will give you the geometry profile, and the DI gives you the ideal diameter. A lot of people design with these still when they're creating parts, and they look at the DI, and we can do those as well. Mat Simulator is actually like a 1D DANTE simulation. The robust utility, you input your time temperature or your rate time data, and you can predict the volume phase fractions over time, and individual metallurgical phases and final hardness, which is really useful in like seconds compared to a full FEA package because you're only solving for one node. And then, like I said earlier, for fitting utilities, you'd fit your experimental data to the DANTE database. We have dilat fit, which is used for dilatometry data, mech fit, which is used to fit the mechanical properties of the individual phases, and then TTT fit and HTC fit are utilities that help us fit TTT diagrams to DANTE, and HTC fit is kind of unique. It needs to use Abacus right now, and it's used to fit heat transfer coefficients based on thermocouple data. So let's start it out right away. We use VCarb. So this is a vacuum pressure carburized scheduler. We can use it to design a recipe. So you can use it to determine a boost diffuse schedule. Is what they call it for the vacuum process. And that'll help you get to the required K-step that you're looking for. It could also be used to predict the K-step and carbon concentration of recipes that are given to it based on the material in the database. It also gives you a hardness of as quenched Martensite. Like we said, we didn't have the other diffusive phases into the mixture law there, so we put in the as quenched hardness so we can know what you would get out of it if it was 100% Martensite. And then, so the process inputs here, we have material, geometry, and process is the main thing here, and then some controls. You're looking at the process screen right now, and this will let you know what we can input in here. So we have like some furnace roundup time, so how long it takes to get to the pressure level you're looking for, or carbon level you're looking for. We have the carburizing temperature, so what temperature you're carburizing at, partial pressure in the chamber. The important guys here are like the effective K-step of 1 millimeter here, and then the carbon at that level, which is 0.4 carbon. And then we have a monitor point, which helps us control the boost and diffuse, how long it boosts for and how long it diffuses for. And then those help put into the upper and lower bounds. So it'll boost up to that 1.1 for this one, and then it'll diffuse down to 0.7. And then the final surface carbon, like what you want on the surface. And then you analyze it, and then you hit plot, and then you get the plot of the actual thing here. And actually shown, make sure that's on screen. Move down, there we go. So, oops, go back. All right, and then so actually shown here, we have, I have put indicator lines here at the 1 millimeter depth mark and the 0.4 carbon. This was the target. Our final diffuse here puts us a little bit above that, which is kind of good. You always want to be a little over than a little under, right? And that shows exactly what it would be. And this would be the hardness of the as quenched Martensite at that point. It also has, like I said, material, geometry, and controls inputs. So the material inputs use the DANTE material database. Right here we use 4120, so it's 41XX, and then it's 20.2 base carbon. And then we have a grain size calculation and nominal and modified alloy. So if you have a different alloy melt, we can account for that, and it'll change depending on the alloy melt. For geometry, we have a geometry effect. So an outer radius and an inner radius will accept carbon at different rates. And so we applied that geometry to it. And a load surface area, which also is kind of define how much a gas is used during your process, during the boost schedules. And then the model thickness is like how long it needs to calculate for. So this is like how deep your model is. And then as far as the controls, we can change temperature to Fahrenheit or Celsius. We can do time in minutes or seconds. We can do your standard imperial units or SI for all these type of things. We have a gas type factor that if you're using acetylene, we usually leave that as 1. But if you're using some lower grade, let's say propane or something like that, you want to bring that number down a little bit in order to account for how well it can carburize. And that's pretty much it for VCarb. GCarb works pretty much a similar way, only you're not going to use boost diffuse schedules. You're going to get time, temperature, and a hold for the carbon potential. So it's a scheduler. We can be used to design recipes. So here we see we define 2 steps, and then we say the third one is to be determined for how long it'll take. And then we define temperature and carbon potential at those steps. Not too much difference. Same roundup time, same effective K-step that you would need, the carbon at that K-step, and then the total number of steps. yeah, and that's gives you the same kind of output here. It'll give you the Asquince Martensite hardness. And for here, we were targeting 1 and 0.45. So that one pretty much nailed it. The other inputs, the material geometry and controls inputs are pretty similar. Again, we use the material database and normal grain size, base carbon. This one is 4110 is what we ran that as. Again, geometry outputs, we have the outer radius or inner radius, the part radius, and the thickness. And then we have the units that we can define for all those. And GNitro works the same way, but for a nitriding process. So nitriding works a little bit different, but we still kind of use a nitrogen potential. So it's kind of like the gas carburization one we just did, GCarb. And it'll predict the schedule. You can predict a step to be determined, or if you give it all, it'll actually give you a prediction of what the profile will look like, the nitrogen profile. The nitrogen profiles are usually more narrow or shallow. And you can see here, it actually has nitride information. So you can see that the nitrides are on the very near surface at the end of this process. And it works in pretty much the exact same way. We have material definitions based on the DANTE material database. We have geometry, and then we have units in the controls. So for the next one, we have TTT generator. So it's it'll produce a TTT or a CCT diagram. It can do both. Here we see a TTT diagram. So time, temperature, isothermal data here. And you have the material inputs from the database, and then total carbon content, and grain size, and alloy composition. So you can get a TT diagram based on our parameters for any of those options there. So the process inputs include upper and lower temperature bounds. Do I have a slide for that? I do not. Same way though, they choose the upper and lower temperature bounds. So it's basically how tall to make the graph and how low. So this one would be 750 to 300. TTTs don't have Martensite transformation, so otherwise we don't have that line there. And the isothermal hold time, so how long to span the x-axis for you, and the shortest cooling time, so how short, 1 second here, 10 seconds there. And then if we were to modify this chemistry here from 4120 to 4140, you can see you expect that the phase diagram would move to the right. And as you can see, using the same marks, we move completely out of the ferrite and perlite, which is at this top level here, and we move more into the bainite areas here. The green is the bainite, and the purple is the ferrite and perlite. Hopefully that makes sense for you. So the variation of alloy composition is applied in here, and this slide kind of shows the difference in changing a little bit of extra moly. Actually, it's a lot of extra moly in here, and how it shifts the diagram. You can see this is from 0.2% to 1.2%. And so different heat and different bars will have different alloy composition. And we needed something to account for that. And so we created this alloy composition algorithm inside the TT diagram, so we can see the change in that. And then so the grain size kind of works the same way. You can see the grains here, we had a larger grain size, and you can see the difference in the phase transformation timing here. It is very slight, but you can still see the difference in between it, since it is only an extra 0.1 millimeter size grain. But there you can see this is at 1 second, and then here this is later than 1 second for the 1% bainite nose. And larger grains will increase hardenability. So, this is the CCT version. This is still TTT CCT app, but this is the CCT plot. You can change that in your analysis type here. And then so this is more continuous cooling. So here we have a number of cooling curves that we applied. We specified one at 20 degrees C here. Yep, 30 degrees. 30 degrees C per second here. And so that's this rate here. And if we cool at that rate, then we miss the bainite nose here, and then we hit just the martensite, which is kind of what we were going for. And so that's the TTT generator. Now the inverse of that is the CHT, continuous heating diagram here. And this is evaluates the isothermal or TTTH or rate-based CHT austenite transformation behavior. So for processes like laser or induction heating, the austenite transformation is very rate-based. So we need to know how long to heat in order to get a full transformation to austenite. And this tool is made for that. So it works the same way as the TCT diagram. You use your material selection. You'd have a prior tempering temperature for your martensite, because that does affect your austenite start. You have your initial phases, which are very important. We'll talk about those in the next couple slides. And you grain size, color composition, same way as the DANTE material database. Excuse me. This will also do carbon and carbides. You can see carbon and carbide A and carbide size factor, because it does carbide dissolution for that rate-based calculation as well. So the controls inputs are a little different for this. It's more of the DANTE, the full package controls, where we have maximum limits on maximum phase change, time, and temperature, and carbon change per increment in order for it to calculate all these properly here. And then, like I said, we do carbon separation, carbon decomposition. For Jomini, Jomini does the Jomini end quench predictions. So what we'll get here is we'll get the individual phases over Jomini point. Jomini point is depth, and I believe each one of those is about an 1/8 inch. So your material inputs are exactly the same. You know, from the database, choose it. And then it runs the Jomini end quench. And from here, you can see you have some bainites being formed right near the surface. You have a lot of martensite, this black line here. And that tells you how much percentage here. You can see the phase fraction on the right. So at the very surface, we have 100% martensite, and then it goes down. Actually, we have a little bit of bainite too. And then it drops off as the bainite comes into play. And this will help you design. A lot of people use Jomini in design. The DI predictor we're still working on the GUI for it right now. But right now it's executed from a DOS window, the script base. And so it'll tell you the ideal diameter based on the input parameters, the same input parameters we just showed for the Jomini. And it uses the bar end, the Jomini, or the DI predictor, the ideal diameter to solve for all that. And so for this instance of 4120, we have an ideal diameter of about 58 millimeters. So then we have a mat simulator. So MatSim, like I said, is phase hardness and strain predictions for heating and cooling curves that we define. So thermocouple data and stuff. Material inputs are, again, same material inputs. I've been beating in on you guys, I'm sorry. So we use DANTE grade, material grade, use carbon and carbides. It has a carbide dissolution and separation models built in here. And this is for a 1D analysis. So this is just time temperature data for that point in space. Process inputs include the initial temperature, and then heating and cooling thermocouple data and stuff that you can input as the process tab. From here, we see, don't have the temperature on it, but we do have a process of 4140 here. And we can see the yellow line here starts, this is the austenite, so we have a heat up. We have initial phases of ferrite and perlite, which is the blue and the red line. They drop down to 0 as the austenite is formed. And then there's a quench here, and you can see when the quench starts, we have a martensite transformation and a tempered martensite transformation happening at the same time. And when it finishes off at the end of the process, it looks like it's maybe about the 1% retained austenite, and the rest is martensite and tempered martensite. Just trying to read the graph. The final hardness was predicted right down here. We give the final hardness based on the metallurgical phase. It's that mixture law that we were talking about earlier. and that's came out to be about 52 HRC. You can change it to Vickers, I believe, in the inputs as well. So time temperature data, how do we get it? You can use thermocouples. Here we have an experiment that we ran with one of those furnaces. So for the accurate determination, we needed to know what the surface temperature was over time, what the core was over time. And so we use this rig with thermocouples to find that time temperature data. You can use this for pretty much any parts. If you have parts that you're heat treating, you can drill a hole and put it in there. We prefer drilling a hole over attaching them to the surface because you can get like a fin cooling effect with thermocouple at the surface. And this is like kind of what the data you would see. You see this purple line here. It quenches really fast, so that would be indicative of like a surface thermocouple here. These ones will be more closer to the core, and then closest to the core we would have these ones. And you see there's a little bump in the time temperature data here. This is because it's a latent heat. There's a phase transformation going on. Based on the temperature, it's probably ferrite or perlite, or maybe very close to upper bankite, but you know. And that latent heat is very telltale. We see that a lot. It's actually good stuff for us. So then the MatSim can also do, like I said earlier, temperature and strain. So you can do what we normally would see for dilatometry data. And we can use this as rate dependent for austenite formation. We have tempering kinetics, like I said. And then these are controls that limit the max amount of phase change per substeps. And so this is like something to give you better resolution as you get your plots done. We also have a carbon separation model. So when you transform to ferrite, you get a carbon rejection, and that has an effect on the Martensite start. It'll make it lower if you have more carbon. And then you also have carbide decomposition. So if you start initially with carbides, you decomp and you have a higher carbon level in the austenite solution before quench. And then you can change your hardness units from HRC to Vickers. Now, let's talk a little more about dilatometry data. So dilatometry experiments aim to measure the dimensional change of a material. So they heat up a material and they have a measurement on it, and as it heats up, you can see that in this heating section, it actually grows, right? And so once it reaches austenite temperature, it'll drop a strain, a dilation, right? And that volume change tells us a lot about the austenite formation, when it happens, what time, how big the strain is. That's why we prefer like the dilatometry data when we fit these experiments, because we can get a lot of information from it. And then you start to cool after that, right? And then you cool as you're quenching. And when you see one of these changes in down at the bottom here, where the MS pops up, you see a change in dilation. That is the change in strain is a phase transformation. And we get a lot of good data on that. So what temperature it started, how much is the whole strain, and everything. And in steel, these tests are really useful to determine the phase kinetics and the transformation strains. And then this shows one loop over and over again, but you'd probably do several loops in order to get fully characterize the base material and everything there. So like the next loop would be all Martensite, and we would know that would change the shape of this curve a little bit, because each one of these phases has different coefficient of thermal expansion. So with the same, I was just talking about the same sample and the heating rate, the different initial phases cause a significant variation here. And so during this, the initial phase was an annealed phase here as it comes through the first cycle. And we see our austenite starts, happens at whatever temperature this is, and it finishes here. And then when we come through again, we now have Martensite. And so Martensite needs to temper. The carbon atom needs to come out of the lattice, and you have a volume shrinkage here as you're tempering the Martensite. And then that changes the effect of where your austenite formation is. You can see it's further at a higher temperature. It's further on down the line here. And that's really important to know, and that's why we usually run a dilatometry test a couple times in order to get that data. So here's more about the initial phase. So if the initial phase here, we could start with, say, initial phase with perlite. And they all start on this gray line here. The overlap is kind of misleading a little bit, but they all start on this gray line here. And the blue line, you can see there isn't very much variation. It's pretty much a straight line. Comes up to AC1, starts creating austenite, finishes austenite, and then we start cooling down, and we get martensite. And then the second one is the orange thing here, and there was a high temperature martensite. So it's already pretty much tempered almost completely. You can see the orange line coming through here, and there is a little bit of a dip here at the higher temperatures, past the tempering temperature, and then the austenite start is a little bit different. And then the gray line is actually low temperature martensite, so it happens in temperature at like maybe 250 or something around here. And then you can see the effect on the is no longer a straight line anymore for the coefficient here. You have definitely a volume shrinkage. And then it changes where your austenite is. And they all end up in different places here. Once you cool them down, we all go to martensite, and we all come back here, and it's all in a different end strain. And that's really important for the DANTE models. Next, we have forming a ferrite. So this is carbon rejection we were talking about earlier. So when we cool down here from austenite temperatures, we're all at the same temperature on the image to the right here, left. And as we cool down, we do an isothermal hold at 100 seconds, 130 seconds, and 200 seconds. And the longer isothermal hold generates more ferrite, which rejects more carbon into the austenite matrix. And you can see the effect on martensite transformation, the martensite start right after that. Whereas like as you hold it for 200 seconds at ferrite, the MS is now down to almost 325 or something like that, or 330. Whereas if we held for only 100 seconds, the martensite start is at 400 seconds, or 400 degrees, I'm sorry. It's a big deal, big difference and that's why we added it to the DANTE model in order to account for that. And material, yep, covered that. All right, so carbide size. So I was telling earlier that we have carbide dissolution model, and I mean, logically, larger carbides take a lot longer to dissolve than smaller carbides. The types of carbides, if they're spheroids, they take a little longer than like plates, like through Ferrite and everything. So here, this shows the model here using a little bit of matte sim. The red line is the heating up temperature. And then so the difference between the upper left and upper right is the heating, the soaking temperature. We go to 850 on the one on the left and 950 on the one on the right. And they have the same amount of carbon, same amount of carbide size, and the carbide total carbide amount. And you can see how much longer it takes for the 800 to get to that temperature, or get to that carbon level. Now the two images right below have a difference of small and large carbides. Obviously, you can see that the small dissolve really quickly into the matrix. You know, you're leveling out at about 300 degrees or 300 seconds, whereas a large carbide, you don't even get close to the carbon level that dissolving them all. So knowing your carbide size and knowing that prior hand is really useful. That ultimately has an effect on martensite transformation behavior. And you can see that in the image, the bottom left, the different martensite transformation caused by the different soak conditions. So more carbon will decrease the temperature at which martensite starts. So for tempering, high temperature tempering and annealing processes, there is a volume shrinkage when you carbide growth and forming and coarsening. And you see this through the strain volume tempering over time. Graphs below, you know, carbides originally, they start to form and they start to grow, and then they get really coarse, and you can see the volume fractions, the difference between them. It first really grows and then it starts to shrink down. And you can see that through those graphs there. So what does it all mean? Now we're getting to the fitting utilities, and I need a little bit of background for dilatometry. So we can see here we have a Martensite fit through our dilat fit program. And we can fit austenite to ferrite, perlite, bainite, or martensite, or all phases. And then we can evaluate the Austenite transformation behavior with it. And it all fits into these DANTE parameters. Like right here, we have 4 parameters for both the Martensite fit, the new alpha, beta, epsilon, and a Martensite start, which is really, really important here. So you can get this through experimental data, through dilatometry data, and then you can fit the data with this utility to the DANTE material database or the user database and create your own material based on these. And you can see here I have a little bit of a animation transition between the two. This fit wasn't exactly to our liking, especially on the lower temperature end. So we ran a loop with 100 iterations and try to fit it a little better and increase the Martensite temperature, and the magic works. And we get a much better fit based on that. You can see here the loops. So you would choose your phase options, so what phase you want to fit to, your kinetics fitting model. So here we did a random search with 100 loops. And then since it's Martensite, we're fitting to temperature here. We can also fit the time as well for isothermals. And then, so MechFit works, again, fitting utilities. Here, there's a lot more parameters to fit through the database. And this is for the individual phases, the Martensite. At this one is for Martensite, but there you fit the individual phases to the stress, strain rate, and temperature, and carbon content. It's all a function of all those parameters. So the mechanical properties can get a little deep as far as fitting. So you define your temperature, your Young's modulus, and Poisson's ratio. You're basically your elastic conditions, and then you would fit it to your data for the plastic conditions. And then we use a fitting where it's an initial guess and then a lower and upper bound to kind of control where you would fit that data to. The same thing with the dilat fit. There was an initial guess and then a lower bound and an upper bound to fit to. And then the last two we don't have any images for, but what I'd like to talk about them a little bit. It was a TTT fit and HTC fit. Both of them are having GUIs being developed right now. Right now they're executed through a DOS window, and the data can be plotted through Excel or any other plotting software that you have. So TTT fit will take like a TTT diagram that you have for your material and fit them to the DANTE parameters. They're really good for predicting the phase transformation timings of the diffusive phases, right, perlite, phase, bainite, and but it doesn't offer any information as far as the Martensite transformation behavior, like the MS. Obviously, because of the nature of the TTT, it's a isothermal hold, and Martensite isn't included in that. So usually that time, the Martensite start time and end times are usually provided, the MS, and then you don't get any information about the transformation strains, which are really important as far as distortion prediction. The HTC fit is another one that's pretty powerful, actually, but you need to use a Abacus DANTE model in order to get it combined with it. Right now, it's currently not available for ANSYS. Maybe in the future we can write a little more to it, but it's used to determine heat transfer coefficients from time temperature data, so your thermocouple data, or model data or something like that. You can determine what HTC was used, heat transfer coefficient on the surface of the part, and it really works really well as far as fitting those HTCs. I think that's all I have time. I might have hit the time just about right here. If you need any other questions or anything, you can contact me. I'm Jason Meyer at DANTE Solutions, or you can just send an email to our general box. Everybody, like I said, we're a small engineering firm. We all get the emails for support, so you can send that to us or give us a call.
Awesome, thank you very much. And for folks on the phone, I think you can see exactly why we're happy to have DANTE as a member, as they fit right into the the materials, processes, and systems mantra that we've been talking about. If you do have questions, we have a little bit of time to take those, so please use the fire them away with the Q&A function on the Zoom taskbar there, and we can ask those and certainly get them answered. If we do run out of time, or if you have a more specific question, would encourage you to reach out to Jason and the folks over at DANTE to answer whatever you have a little more in depth. or more specifically. So a couple of questions that came in, Jason. Wanted to, there's a lot of, simulation material that you went through, but are there, can you summarize what materials in general we're talking about that can be analyzed? Is there any limitation there in terms of the kinds of materials we're talking about?
Sure. I mean, our models are based on steel grades, so carburizing and hardening steel grades. We have a precipitation model for precipitation hardening for aluminums and nickel-based alloys. We are lacking at the data right now on that, but because we just haven't had the energy or the time to actually have experimental data run on those types of things. But the model is implemented. If somebody does have the data, we'd love to collaborate and work together on getting that work.
There you go. There's some opportunities there. In terms of the quenching rate, can you talk about the upper and lower ranges, the range we're talking about in terms of the quenching rate and how much what you can analyze there?
Sure. I mean, it's pretty much any quenching rate you can apply, because if you apply a too high of a quenching rate, you're basically controlled by conduction at that point. So anything you can pretty much do. We done stuff from intensive quenching down to air cooling with aerospace grades and stuff. So anything, and we use a blanket HTC on our surfaces and stuff like that in order to define them. So you can have a low heat transfer coefficient of, like, say 10 for air cool or something like that, and then go all the way up to whatever you can do.
Right. Have you ever, or can you analyze these materials in, zero atmosphere or zero gravity?
Well, I mean, I don't know about zero G. That's kind of interesting, to be honest. But zero atmosphere, I mean, we do the vacuum process, so it is kind of similar. It'll be pretty interesting. Might have to look into that.
Excellent. Again, if you do have questions, please go ahead and fire them away at the Q&A session, the Q&A function on the Zoom taskbar. We have a little bit of time left to do that. There may be some non-engineers that view this this webinar. Do you have a like myself? Do you have a link or anything on your website that might provide some definitions of some of the acronyms that you went through today in terms of what they might mean for people?
Sure. Yeah, you find a lot of information on our website. We have a lot of papers and other information as far as like what we do and how we do it.
Okay.
You can definitely go to DANTE Solutions. There's several tabs there, and we can. We also have case studies there that we do from time to time that are really useful for industry. Induction heating and stuff like that. Some of the recent ones. Immersion quenching and other stuff like that. So people aren't normally experienced with those kind of things. And I know my talk was pretty technical, and so
right.
I apologize for that for the layman's here in the audience. But you can find a lot of that information on our site, our website.
I'm sure most of the other folks tuning in are more well in tune with those with a lot of the terminology and acronyms than I, the non-engineer, might be. So just want to ask for our other friends out there in case they might be viewing. So we ran through a lot of things today. Are there any other benefits or limitations that you could speak to in terms of the solutions that you're providing that you went through today?
Sure. Well, I mean, the benefits
and the bad, I suppose.
Yeah. The benefits are in time savings, cost savings. Obviously, DANTE is best used early in the design process, so you can really fix these issues before they happen, quench cracks and stuff like that. And modeling is paramount for that. So benefits are good there. Limitations, I'm not exactly sure. I'm sure there's a whole bunch, but it's really hard to pinpoint right now. But we do use right now is steel grades, and like I said, we'd love to get more into the precipitation model and everything along those lines.
Right. I know that was a little bit of a tough question, but you know, no one wants to talk about the limitations. So I sprung that one on you. So
Yeah.
thank you for your candidness there. So again, folks on the call, please are participating or watching this webinar later. Please reach out to Jason with any additional questions or comments you might have. Thank DANTE, thank Jason for their membership. I want to thank them for their presentation today. I do want to encourage folks to reach out to them. Again, please stay tuned to your emails from Lyft. Give us a shout if you have any questions about our organization or need to reach out to Jason for any other reason. Encourage you guys to stay tuned. We are, you know, this is mid-July. We did have this webinar scheduled. Thank you to DANTE for participating. Slowing down a little bit our webinar series in the summer as folks are taking time off and on vacation, but we'll ramp back up in the fall. So please stay tuned to our website and your emails for those. In the meantime, Jason, thank you very much, and thank you to everyone for tuning in today. We appreciate it.
Yeah, thanks, Joe. Appreciate it.
Awesome. We'll talk to you guys next time. Thank you.